Assalamualaikum everyone. Thank you for coming. Thank you so much, sir, for the kind introduction. This is the, as both of the respected professors said, that this is the first lecture. So, my idea of this series is that I'm not going to teach you guys, but we are going to learn from each other. I share my point of view, my practices, my style of teaching, and I deliver a lecture, and I be open for your feedback as well. So we are here to learn from each other, we can share experiences, and we can share the pedagogical skills, and we can benefit from each other. So the whole idea is, of me being here is that I am very eager to learn, and I am very eager to gain experience. So I am open to questions, both related to this topic, the technical questions, as well as you can ask the technical questions by interrupting me through the lecture, during the lecture. But about the pedagogical skills or about the feedback, I prefer that you may write your feedback down and we can discuss it at the end of this lecture. The topic I have selected for today's talk is basic computer architecture, how a processor works. And this is in fact the first lecture of my regular course that I teach every year, the course of Microprocessor Systems. Because the reason for choosing this lecture is because this lecture is going to set the momentum for the rest of my course. And it is a very important course in electronic engineering degree. It was a difficult task for me to, as Professor Zadi said, that we have to instantly get the attention of the students and we have to instantly satisfy them. So this lecture will set the tone, is going to set the tone up for the rest of my course. And it is very important that I discuss this crucial lecture with you guys so that I can get a feedback. Because in hardcore technical topics, it's a different level of pedagogy. But in the general topics like this, where we are setting the tone for a whole course, it's going to require some extra effort, some different types of skills. So I selected this topic for this task. And I always start with this slide, or a similar slide in this course, that why are we studying this course? Why microprocessors are important? What's the significance of this course in our lives? And the simple answer is that microprocessors are everywhere. You look around you, you will find a lot of modern electronic gadgets, and there is a 99.99% chance that there is a microcontroller inside or a microprocessor inside that gadget. Even this pen has a microcontroller inside it. Your smartwatch, laptop, this pointer, microphone, you name it, you name a gadget here, the camera, your home appliances, augmented reality, drones, robotics, solar inverters, even the regular automobiles have microprocessors, and the self-driving cars, AI, everything has a microcontroller and a microprocessor inside it. And in today's era, we talk about AI, machine learning, the importance of programming languages, but what's running those programs and those languages at the back end? It's the processor. Without a processor, we would have been living in 1800s. So it's the processor which is running, which is executing all those programs, those tasks, or that machine learning algorithm, or the AI, or the image processing algorithms. Everything is being run on the microcontroller or a microcontroller. It's a very, very important course, and it wouldn't be wrong to say that the world around us is built around microprocessors, because everything is running on microprocessors right now. So this is the significance of this course. And in the first lecture, as the tentative audience or the actual audience, the students have already heard the course of digital logic design and the programming languages. So they are familiar about programming in general, what is a program, what are instructions, and the concepts of memory and registers. So we'll build on that and we'll see that what is inside a very basic processor, how a processor gets the information, processes it, and gives us the results. So let's move to that and start with the definition of a computer. Computer, the term itself, is its definition. Something or someone who computes. And if we go into detail, as per the most widely accepted definition, there are certain prerequisites that must be fulfilled by a machine to be called a computer or to be categorized as a computer. If a machine or an electronic device has these traits, which are the traits, it can perform high-speed operations or process information, and it is a programmable device. These two are the core requirements. So if a device is programmable and it can perform high-speed mathematical or logical operations or otherwise process information, it may be categorized as a computer. So now we know that something or some device to be called as a computer or to be categorized as a computer, it must have these traits, these two basic traits. But to have those hardware level, it must have certain components, certain hardware parts. For instance, we know that it should be programmable, right? So to be programmable, the program needs to be stored somewhere, and for that it needs to have a memory. In the memory, the program will be stored. The process, the information will also be stored. There are different types of architecture, but we'll assume that there is just one memory for today's lecture. And the second requirement was that it should be able to process information. And to process information, we need to have a processor which processes the information. So these two core requirements force us that the computer must have a processor and a memory. But there is a third requirement mentioned here, which is also mentioned as the must-have part. The fourth one is optional. This is not optional. Input and output device is not optional. Why? It wasn't in the definition. But just think about it, that this smartphone also has a processor inside it, and there is a touch screen. This touch screen is your display, which is the output, and the touch system, which is the input. Just assume that there was no touch screen in this phone, and everything else was there. Would it be useful? If there was no input and output, would it be useful? There would be processor, there would be camera, there would be everything else. But if it is not able to communicate with me or its surroundings, if it is not going to get information from somewhere, process that information and display or send the result to the output, the processed information, the device will be useless. So the processor and memory are the core parts, but the input and output devices are the must-have, because from where are we getting that information that the processor is processing? From the input. And what are we doing with the result, that processed information? Where are we sending it? If it is just processing it and keeping it with itself, it's going to be useless. So the input and output devices are also a must-have. These three parts are a must-have. Storage is optional. There is a slight difference between memory and storage. Storage is usually, the term storage is used for the permanent storage, where we need to log the data or store the data permanently for the longer term use. But it's not the core requirement for a processor. A memory would do the job for temporary data processing. So now we know that a computer should have three major parts: processor, I/O devices. I/O means input-output devices, and a memory. So we look into the block diagram, and then inside each of these parts, that how they are interconnected and how they exchange information with each other, and how the cycle of the information processing works. So based on our definition, we have developed a block diagram from basic computer. We can see that this outer box, this white box here, is for computer. And inside that computer, we have a processor, or what we generally call a CPU, a central processing unit, a memory unit, and some input and output devices, where the storage device is auxiliary. It can be an SSD, hard drive, USB, SD card. These are all storage devices. Our cell phone works without all these devices as well. The memory unit is core, and it's a core part of the computer. Input devices may include some sensor, some push buttons, a keyboard, microphone. All of these are input devices that are providing signal or information to the processor. Then this processor or the CPU processes that information. How? We'll come to that. And then if the processed information, the result of that processed data, is displayed through an output device. It can be a display for the user, so the information can be displayed in physical. This is an output device. It can be just a single pin to turn on or off a fan or a light. It can be a speaker, or it can be any other thing where we can send the output or communicate with another device. This is an output device where I am sending my data from one device to another device. So it is also an input-output device. So input and output devices themselves are not part of the computer, but they are core requirement for a computer-based system. The computer itself should just have an option to enable input, getting input, and to enable sending an output. So we'll talk about the portions inside this white box. The memory unit, I'll come to that. We have already talked about memory in our previous course. We have already designed a memory addressing system, but I'll briefly overview the memory again. The main focus of this lecture would be this control unit and the arithmetic logic unit. As we said that the processor is the brain of the computer, which actually processes the information. So what do we mean by processing the information? What comes to your mind when we say process information? What kind of process? What is a process? What do we mean by processing an information? What is an information, by the way? Some data that is coming from somewhere. It can be a data from a sensor, it can be an input from a user. And to process it means that we are performing an operation on it. Operation, but which types of operations are possible? Logical operations, and or not exclusive or shift, rotate, arithmetic operations, addition, subtraction, multiplication, division. Is there any other process or you can say operation that comes to your mind? Can you name any arithmetic operation other than addition, subtraction, multiplication, and division? These are the core. If someone is thinking about integration or differentiation, it is basically in digital domain it is summation and integration, summation and difference. So all the mathematical operations can be performed using these four basic arithmetic operators. And same goes for the logical operations and or exclusive or and not. And the rest can be done through the combination of these operations. So the arithmetic and logic unit is actually the processor. This part that we designed from scratch in our last course is actually the processor. Let me go to this slide and I go back to the previous slide again. This is the area. I copied this slide from our DLD course. The arithmetic and logic unit has an arithmetic circuit, a logic circuit. It has certain inputs, the data lines, where the operands come. The operands are the data that is input that need to be processed. So the data is input to the data lines. These data lines, as you can see that A and B are data lines, they are connected with the logical circuit as well as the arithmetic circuit. So there is an option that what function we want to perform or what operation we want to perform on this data. It may be an arithmetic operation, it may be a logical operation, or it may be a shift operation. So we have to choose, we have to select, the user will have to select that what kind of operation we want to perform. And how do we select them? Based on our requirement. Like sometimes we need to find the difference of two values, sometimes we need to integrate two values. So accordingly, the user will give a command to the processor and it will, based on that command, based on that instruction, the user will instruct it and it will select that operation. So we have some select lines. I will instruct, okay, do this. I will instruct who? The processor. And inside the processor there is a control unit. The control unit will understand my command and it will decode the instruction and it will understand it, okay, I have been instructed to do this. I have been instructed by the user through a command to do this, to select the addition, let's say the operation of addition in the ALU. So on the select lines, it will generate a signal, ones or zeros, it will generate a signal here and it will select one of these multiple operations that are possible and through these multiplexer, it will send the result to the output, to the display or to the other device. Yeah.
I think it would be better to say example के साथ explain हो जाए. Like for example, I want to give an input to the processor like 2 plus 2. Give me the answer. तो इसको कैसे आप इसके अंदर कैसे वो resolution आप?
Yes, I'll come to that. I'll come to the example as well. But very shortly, I'll come to the example because for now I'm going to just explain the function or the purpose of each block. The function of the control block is to understand my command and generate some signal. To understand my command and generate some signal to select the appropriate operation.
Function can easily be understood. For example, I think.
Okay, for example, you may have only 4 mathematical operations, right? So the user says, add, how many operands do we need? Minimum number of operands do we need for addition? 2. Okay, so I have to give the information. If I say add what? Okay, add x with what? I have to give information of both. So add x, comma, y. Now it will know that I am going to add x and y. What is x? What is y?
We have to tell them.
We have to tell, or it should know. If I say add x and add y, it should understand what is x and what is y. And that's where the memory comes in. Our third basic part. When I say add, now if you see this is an instruction. This is an instruction by the user, right? The instruction is saying add, the user is saying add x and y. Okay. So the user has told the processor, I want this. I want the sum of x and y. This part is telling me what? The operation. And this part is telling me what? The operand. So an instruction, the instruction sent by the user must have information about two things. What I want, and what operation do I want to be performed, and the operand or the data on which I want that operation to be performed. These two basic information must be a part of the instruction. This operation part will be understood by the control unit. The control unit will get this part of an instruction and it will decode it. It will decode, we know that there is no alphabetical word add inside a computer. There are all ones and zeros. So there will be a code for addition and that code will be decoded by this control unit. And this control unit will generate some signals. It will send some signals to the arithmetic logic unit. The opcode, the operation code will come here. It will decode it and it will give some signal to this ALU to select the add operation using these select lines. Now addition will be selected using the multiplexer. Many things are multiplexed, so we can select one thing out of the multiple things. I have selected addition out of the multiple things. The second part was from where the operands are coming. These two operands are variables, some data. So it is either coming from input or it is stored somewhere. Right? There are only two options from where a data can come. Either I am providing the data in runtime through an input, or it is stored somewhere in the memory. The variable is declared in the memory. Right?
If we are telling the computer to add 1 and 2, then what is the purpose of memory? Because it is not already stored.
Add data. Right? You are saying you are asking the okay. So you are saying add 1 and 2, not some variables. Just add 1 and 2. When you say add a number, from where does that number come? From the user, from the input. So you are pushing a button, you are pushing a key. When you press the key, you are generating a code for number 9. And that code should be read by this processor, and that the code for 9 should travel all the way from the input to this data line. So I have to tell, okay, add 1 and 2, but from where the 1 and 2 is coming? Either from the user in runtime or from the memory. Or it may come directly, it may be directly a part of an instruction. These are different addressing modes. But okay, if it is just 1, what is the code for 1 in binary? It is a number, right? So the code for 1 is, if an 8-bit number is there, 0000000001. So this data will go to the data lines. The data itself, if there is no memory, if it is the direct data, literal data, the data will travel. It will be part of the instruction, so the instruction will be broken.
So the question was, if the instruction, there might be no use of memory if we are giving the correct instruction to the computer.
Okay.
Okay. There may be a role of RAM and ROM.
Actually, if for data, not every instruction will use memory.
You told me
Okay.
that the memory is the integral part.
Integral part, but I didn't say for data storage. I said for program storage. Where the program is stored. From where the user instruction is coming. User is not typing those instructions in real time. You write a program, you load it to the memory. Then you unplug it. Right? So for program storage it is very, very integral. For instructions it is integral, yes, because there will be instructions that are going to use memory. But there may be instructions that are not going to use memory. There are two types of instructions, memory reference and non-memory reference. So if you are going to instruct the memory in your instruction, yes, you need a memory. But for data. But if you said add 1 and 2, you don't need a memory for only this instruction. But there is not just one instruction in it. There are multiple different types of instructions. And for those, you need to store temporary variables as well. You need to store temporary result as well. If you want to add 1 plus 2 plus 3 plus 4, you need to store the result of first 2 and then add the third digit into the result. So where will be the result of the first 2 in the memory? Right? But the basic first purpose of memory is to store the program. We are coming to that shortly. Okay, so the instructions opcode is in the control unit, and the operand goes to the ALU if it is to be processed, and the control unit selects which operation is to be performed, and the result is either stored to the memory, or it is given to the output, or it is logged or permanently stored in the auxiliary storage if it is available. So how does the control unit work? How a memory works? ALU we have discussed. This is the block diagram of an ALU, and we designed it from ground zero. From ground zero we develop this diagram. What is inside this block we have already designed it ourselves. All these things, they are connected through a common bus. They communicate with each other. Because the data is flowing from one part to another part, there is some input, there is some output, the processor and the memory, so the data may flow from here to here, and then from here to here, and to here. So we need a common system or a common data path for the flow of information. Advantage of this using a common bus, I could have connected this with this directly, this with this directly, this with this directly, but there are hundreds of parts. This is just a basic diagram. There are 4 parts. So there are hundreds and billions of registers in this computer. So we just imagine, I'll give an example, that we want to go from GIK to, let's say, some street number 30, house number 39 in Beria, in Islamabad. So we'll leave GIK, and then we'll take the link road and to the motorway, and all the other vehicles are also taking the motorway, and then we'll take the exit and we'll go to the Beria exit, and then we'll go to our street number. Just assume, so this motorway is my bus. This motorway is my bus, and these are my street numbers and some link roads. Just imagine that there was a dedicated road from every single house to every other single building in the world. Would it be possible? There are millions and billions of houses and buildings in the world. So we cannot physically connect them. It is impossible. There would be a network of roads, maybe extending to the moon, but it would still be impossible to connect each and everything with each other. And that's what's happening inside a microprocessor. When you say, my computer has a 16 GB RAM, all of you would have heard about that, 16 GB. 16 gigabytes of RAM, 16 billion locations of 1 byte each are inside that memory. So it is impossible to connect those 16 billion locations with each other with a dedicated connection. So we have a common bus for that to connect everything with each other. And the disadvantage is obviously it will be a bit slower, because yes, a dedicated connection will always be faster, but if it is not feasible, we'll have to come to a feasible solution. So now coming to the memory part.
Sorry, I have a question.
Yes.
What is the control unit doing here?
Yes, I come to that.
Because my question is that the input device is getting input from the control unit.
No, it is not getting input from the control unit. It is getting a signal of enable or disable from the control unit. The control unit will tell from where my data is coming to the bus.
No, but shouldn't it be right after the input devices? Because right now I have a screen, right?
Yes.
I can provide some input, the signal will generate, right? But it will not do anything because the control unit is not allowing the input device to communicate directly with the bus at this moment. So the control unit should be after the input device, it should not be before the input device.
No. Actually, this whole system, this whole box can be. You are saying that this is not a control unit.
No, you're not saying
There should be a switch, you can say.
No, I am saying that the control unit should not be
before the input device. No, it should be because the switch should be between the bus and the input device. Switch is not the control unit. The control unit is controlling that switch, you can say. It is turning it on or off, or it's a tri-state buffer which it is turning on or off. So the control unit, inside this is a complete circuit. It is just sending a signal to enable or disable this device.
So the input devices are different devices. For
Input devices?
For example, I have a keyboard, right?
So there is a keyboard. This is your keyboard.
And that's an input device.
Yes.
So that's actually an input device. The input device is the keyboard. I can press the key, the signal will be generated, but it will not do anything because the control unit is not prompting that input through the microprocessor and into the bus. And therefore, this control unit, in my opinion, should come after this input device.
Control unit is the central control unit.
Yes.
It is generating signals for CPU, for input, for memory.
I agree.
Right. What kind of signals?
What we'll do is that we will carry on with this discussion towards the end.
Okay.
But we are almost in the half of the lecture.
Yes.
Right? So we will, this is a very interesting discussion. And we will continue with this discussion. Right? But I think let him first present the complete picture.
Yes.
Maybe the things will also become more clear.
Or for now, I can change this input device to input circuit, and I can connect my keyboard device here. I think this would, for now, temporarily solve the issue. Okay, so let's call it input circuit.
Let's proceed in the planned manner.
Right, input circuit, output circuit, and the device is connected to the circuit. And then the control unit is controlling the circuit. So the memory unit, as we discussed, have billions and millions of locations inside, and all those locations are registers, and in each register there is some data. 16 gigabyte is 16 billion registers of 1 byte each, so 1 byte is 8-bit data. And for that, now I need an address, because if there were a dedicated connection of each and every house with each other, I wouldn't need an address for anything. I would just take the road and I will end up on my destination without ever needing an address. But in this case, when I have just one motorway, I need an address. Where do I want to go? I'm taking the main bus, but where do I want to take an exit? And in which state do I want to go? So I need to have an address. And that's a similar way a memory is also working. It has an address for each location, but for that address, we have just numbers. We have used the number of register as its address. So if there are 16 billion registers inside a memory, its address will start from 0 and it will go to 15,999,000,000. Or not exactly, but
So last name will be 99.
yeah, no, not 99. It would be 2 raised to the power that. So in DLD, 1 kilo is not 1000, it is 1024. So it would be go to 1023, right? But just for the sake of understanding, let's call it from 1 to 16 billion, right? So this is my memory unit, and if you see here, this is my bus. So I send my address first. This address will go to the memory address register, and the address will be decoded. That what was the address? You hand over your, you go to China, you don't know Chinese, your address is written on a, your recorded address is in Chinese and it is written on a card. You sit in the cab and you hand over the address to the driver, and the driver decodes that address for you. So this memory address register and the address decoder is actually getting the address and it is decoding it in computer's language. So the computer will access that location, just access that location. Now that location is activated. That location is eventually going to have data, or maybe it already has a data. Let's not talk about the instruction right now. I'll come to that. It will have instructions as well, but okay. For now, there is some data here. Either it is already there, and I want to read it. I want to get that data already stored previously in my previous instructions, and I want to read it. Or I have some data that I want to be stored onto the memory. So there are two possible options. Either to fetch the data or to store the data. And that's where the central control unit comes in. When I am instructing the computer, okay, store this data on memory, and where, at which location, store this data on location 30. The user is asking the computer, this is your data, take it and store it at location number 30. So the location number 30 is going to the address register. The location number 30 will be activated, we'll say, and the data 30, the data, whatever data, let's say we call the data as X or D, the data will come to the data register. And from here, the CPU, the control unit, will see, okay, what was in the instruction? I have to read the instruction, location number 30 or write it. So there will be one bit for that, read or write. And we are going to write it, we are going to store it. So it will send a signal of store to the fetch store control, and whatever I have in the data register will move to that activated location. That's how the memory, each cell has an address, and the address will be activated by the memory address register. Here is the example of storing the data on memory location 30. So the first, memory location 0, the first thing is to select that memory location. Go to that address. Address is 0, it will go to the address 0. The decoder will, this is the address 0, the first one is address 0. So the first address will be activated, and then the data is D, it will go to the data register, and then here the signal will come and the signal will be stored S. So the store signal will come and the data will pass through from top to bottom, and it will be written inside this memory location. So now we know how the data moves between different things and can be read or written to the memory. And this is the same block diagram that we previously saw, just a bit more elaborated. So this is your memory unit right here. This is your ALU, arithmetical unit. This is your input-output controller, and here are the devices, so you can say input-output controller. And then this is your control unit. Okay? I changed it to circuit. I think that would have something.
Yeah, because this is quite clear.
Okay. So the control unit has what are these parts. This is the last part of the discussion today, and then we'll sum it up how it all works in collaboration with each other. So we have PC, IR, and instruction decoder, and that's where the memory will store the instructions now. So PC is the program counter. Before that, we can skip it. We can skip it. We have to see this. Before going to the control unit, we need to understand why are we writing a program. There should be some reason to write a program. We write a program to do something, to do some task, to do some work. So a task is the desired work that is to be done, that I want a computer to do. And to perform that task, now here I can give an example. Let's say my task is to control the temperature of this room. There will be a temperature sensor, obviously, because I want to read the current temperature. And there will be a desired temperature by the user that I want to keep my room at, a temperature that I want my room to be at. Let's say it was 30 degrees, and there is a heater and a cooler connected to these microcontrollers outputs, and there is a temperature sensor that is continuously taking readings that what is the temperature. So let's say the temperature is 36, and I want it to be at 30. What would I do? I turn on the cooler to take the temperature down, and if it was lower than 30, I turn on the heater to bring it up to 30. So I write the program. In that program, I will write read sensor. So I have the reading of the sensor. Then I will write subtract sensor's output minus user's input, my desired temperature. So this result, if the result is greater than 0, what should I do? Turn on cooler. Else, if it is less than 0, turn on heater. And else, if it is 0, turn off both. Okay? So now this is my code. I have written some instructions 1, 2, 3, 4, 5, 6. This is a pseudo code, by the way, but let's call it a code. And it is performing my task. So it is a program, and it's a set of instructions. And this set of instructions has to be executed in a certain sequence. The first one should be to read the sensor. I cannot subtract the data of sensor from anything if you don't have the sensor's data. So the first thing is to get the sensor data, then do this, then compare this, and then turn on or off. So it has to be in a certain sequence. The sequence has to be maintained. Okay? The first thing, keep it in mind. And it's a set of instructions. So instruction number 1, 2, 3, 4. Instruction number 1, 2, 3, 4, 5, 6, 7, 8. But within each instruction, there are certain micro operations going on. For instance, if I go back to this slide, when I give it the first instruction, take input and read the sensor, what is it going to do? It is going to send a command to the IO controller to enable the input. The data will come from here to the bus, and then where is it going? I have not mentioned it. Take input and store it where? Probably it will automatically store it to my temporary register. If I am not telling it where to store, it will have a default location where it will store. Okay? So there must be a default location. It is storing it into the default location. So there are 3 steps. Each of these steps is a micro operation. Okay? So a program is a set of instructions, and an instruction is a set of micro operations. And all the computer does is repeat forever, fetch, decode, and execute the instruction. It will fetch an instruction from where? From the memory. We'll see that shortly. Then it will decode it and it will execute it. So how does it work? How many instructions are there? 8. They have to be executed in a sequence. So they have to be stored in a sequence somewhere. Where? The memory. Otherwise, how can I execute these 8 instructions in a sequence? I write it one by one. So a person is sitting there and it is giving commands. So there will be this air conditioner does have a microcontroller inside, and it is already coded with these instructions. So these 8 instructions are already stored in the memory in this proper sequence. All I have to do is I have to access these instructions one by one. I go to the memory location 1. Now memory, about the memory. Now we are saying that the memory is holding both the data and the instructions. So there are two types of computers. In one computer, there are two memories, one for data, one for program. So one is called the program memory, the other one is called the data memory. In this one, I have only included one memory, so let's assume the upper half is used for program and let's say the lower half is used for data. We can divide it unequally, but for the sake of understanding, let's call it the first half is used for data, the second half is used for program. And in that half, these instructions are stored in a sequence. Now, if this is a sequence of addresses, right? Because whatever, now I said there was data stored in the memory. Now there are program or instructions also stored in the memory. And those instructions are also stored in those registers, which have a certain address. So I give an address of instruction, fetch that instruction. Fetch or store. Fetch that instruction from the memory. The instruction will be on the bus. From the bus, where it will go? Where it will go? An instruction has two parts, right? Some part that is telling you what to do, and the second part that is telling you on what data, on what operand you have to perform that operation. So the part of operation of code, the information of operation goes to the central control unit, right? And it is decoded. Let's skip this. Let's move to this. Add x. When I say add x, let's extend it to an example. It will be easier to understand. There is an instruction add x. Where is it supposed to be stored? In memory. And it should have how many operands? 2. But there is just 1. So if I am short of an operand, there must be a default from where the second one comes. So I assume that the second one comes from the process register by default. Okay? If I am supposed to give 2 operands, if I am supposed to give an address and I am not giving it, it will use the default value. And the default value is this register R here, which is the process register. So when I say add x with what? With something already stored in my default register. So what will be the flow of instruction? We can understand from here very quickly. The instruction will be fetched from the memory. I have not shown the fetch cycle here. After fetching the instruction, it will come on the bus. From the bus, where should it go? To the instruction register. Now the instruction has been taken out of the memory, and now I know that I have to execute this instruction. This is my current instruction that needs to be executed. I have to perform this specific task. And you can see that there is an instruction decoder at the output of this instruction register. This decoder will get that information out of the instruction, and it will generate some signals that will to the controller, to the ALU, to the memory, this fetch and store signals. It will generate a lot of signals and it will control all the devices. So this is your instruction right here in the instruction decoder, and it's generating signals. What type of signals will this instruction generate? Add x. Now what is x? It's a variable. And does it say that it is coming from an input? No. So this must be coming from your memory. So your memory has some location x. It's a variable x, okay? It's an address. It's going to be any address, 100, 200, 300, whatever. So let's call it x. At location x, there will be some data. That data will be fetched and taken to the ALU, arithmetic logic unit, because what we want to perform addition, and that addition will be selected using the control unit. So a signal will be generated, an address x will be sent to the address register, the x location will be selected, a fetch signal will be given to the memory, the data on location x will be taken out and stored to the data register, and then it will be taken to the ALU. So ALU, one data, the second data is in the processor register, it will also come to the ALU, and then the ALU will perform addition of both, and where will be the result? Just a wild guess. When I am not telling it where to store something, what is it doing? Using the default, yes, R. So the result will move to the default register. This is the flow of just one instruction. It was fetched, it was decoded, some signals were generated, and then it was executed by actually performing those operations. And each of these arrows is a micro operation. So that's what I meant when I said that an instruction is a set of micro operations, that one instruction is performed in multiple steps. And what are those steps? How are we controlling that? Using a clock. It's a series of ones and zeros, so at every transition, one operation is being performed. So this all a computer does is fetch, decode, execute, fetch, decode, execute, one instruction, and then second instruction, and then third instruction. And how would it know? I skipped this thing. The program counter. What is the program? Set of instructions. The instructions are stored in a certain sequence. So that sequence will be determined using a counter. What does the counter do? Counts. It keeps counting 0, 1, 2, 3, 4, and this is your counter, which is generating addresses for this memory. So it is fetching first instruction from 0, then 1, then 2, then 3, and it is repeating it in a sequence. So that's how I hope you would have got a bit of idea about how a processor works. Technical part is finished about how a processor works. Next up, I would like to take just 2 to 3 minutes to discuss about what are the latest trends in this field, what we are doing. So basically, the core concept of all the processors is same. All the processors, all types of processors work with the same basic working principle. Some have 2 memories, some have 1 memory, some has 2 buses, and so on. So just the architecture differs a bit, but the fetch, decode, execute remains the same. Why are we interested in what's happening inside a processor is that we want to improve the performance of that computer. And what I mean by performance in a layman's term, when you are going to buy a computer or a cell phone or any computing device, the first thing you see is the speed. कंप्यूटर तेज होना चाहिए, ऐसे ही है ना? लैग ना हो, हैंग ना करे, तो सब कुछ किस पे डिपेंड कर रहा है? The speed of processing. And speed of processing what? The program. The speed of executing the program. So the time taken by a program should be minimum, ideally 0, but time cannot be 0, it will take some time to execute. So what we want to do, we want to minimize this time. We want to reduce this time to whatever minimum value we can. And this time equation is written here. We knew that a program is a set of instructions. So if there are more number of instructions in a program, it will take a longer time. But an instruction is a set of micro operations or cycles. So if one instruction is very long and there are 20 micro operations happening at the back end, but another instruction is very small and there are 2 micro operations happening at the back end, the number of cycles will be lower for the smaller instruction. And the time taken for one cycle. This is the clock speed. After or how quickly that signal is taking transitions. This first term solely depends on your fabrication technology. You would have been hearing general news that the TSMC has successfully tested and fabricated a 3 nanometer node. Previous was 5 nanometer and then for a long time it remained at 6 nanometer. The smaller the node, the higher frequency you can achieve and the lower time per cycle you can achieve. It is independent of the architecture itself, but the fabrication technology. So a part of research is going on in this part to reduce the fabrication, the clock cycle, to advance the fabrication techniques. The second part is in these 2 terms. RISC and CISC are 2 different approaches that are used to design these microprocessors. One of them tries to reduce the number of cycles taken by an instruction, and the other one tries to reduce the number of instructions in a program. 20-second example. If I write A plus B plus C plus D plus E is equal to F, and it is just one instruction in a program, right? My whole program is this, one instruction. And my hardware is capable to handle 1, 2, 3, 4, 5 operands at a time. So my ALU will have 5 inputs at a time. My hardware is complex, but it is going to handle 5 operands at a time. Or I have sent a command, but my hardware is capable to store 5 addresses at a time, but not operands. So it will store 5 addresses and then it will one by one at the back end, we will not know, but at the back end it will take A, B, then add C to it, then add B to it, and so on. So the number of micro operations behind this one will be huge, maybe 20. But if I write A plus B is equal to X, C plus X is equal to X, D plus X is equal to X, and so on. The number of instructions is increasing. But now every instruction is very small. So these are 2 approaches. Cycles per instruction, either optimize that, or instructions per program, either optimize that. You have both options. So these are 2 technologies, RISC and CISC. These computers, the Intel processors are CISC based, your mobile processors are ARM, advanced RISC machines, RISC-based. RISC is the winner in today's era. So in microprocessor systems, research is going on in these domains to increase the core count. There is one processor, it can handle one data at a time. If there are 20 processors, it can handle 20 instructions, or it can process 20 different types of data at a time in parallel. So this is parallel processing. But parallel processing doesn't mean just add a core. It means that the cores should communicate with each other and they should work in harmony. That's where the research part is. Then the other one is branch prediction. I'm not going into the details of that. It is to reduce the cycles wasted, improve the power efficiency. It is linked to the fabrication technology to use materials, to use more efficient low power materials, and so on. AI acceleration, specialized hardware accelerators, and they are optimized for specific tasks, for matrix operations. In our ALU, we had just addition, subtraction, multiplication, and division. What if we wanted to perform 2D operation, an operation in a 2D matrix? We'll form arrays, 1D arrays, and then we'll increment an array and we'll get one data, multiply it, one data, multiply it. It will take a lot of time. So these AI accelerated processors, what they do is they design some task-specific processing units which can handle array-based data at a time and produce a result of an array output at a time. And then we have heterogeneous computing, where we can link CPUs, central processing units, GPUs, graphical processing units, and FPGAs, field programmable gate arrays, into a single chip. Because each of these chips is optimized or efficient for a certain task, but is less efficient for another. So take the advantage of all of them and put them on a single chip. Manufacturing process we have already discussed. In previous days there was a lot of noise about EUV, extreme ultraviolet lithography. Ultraviolet wavelength is very small, so you can have very fine patterns or a 3 nanometer pattern using EUV. So this is manufacturing technology. TSMC has that. Security enhancements, encryption and memory isolation, customization and specialization, which comes with the ASIC domain, application specific integrated circuits, and then the last one is quantum computing, which is completely changing of how a processor works. Because they are using quantum mechanism for computing, and a quantum computer does not work like this. So that's all from my side. I hope everyone will get got some ideas.